Hi, welcome to Maxed Health. And today we're going to be discussing the biochemistry of how enzymes reaction rates and kinetics influence and the influence of xenobiotics, vitamins, and trace elements. Yes, I'm a pharmacist and we have to go into the chemistry of some of these things, the nitty gritties. You need to know it. You can't escape from it. Just for knowledge sake, yeah. So the rate of enzyme reactions is actually measured by the amount of substrate that is changed, or maybe the amount of product that is formed during a period of time. So the rate is actually determined by when you measure the slope of the tangents, like looking at this picture now, when you measure the slope of the tangents to the curve in the initial stage of the reaction. So the steeper the slope, the greater is the rate. So if the enzyme activity is measured over a period of time, the rate of reaction usually falls, and most commonly as a result of the fall in the substrate concentration. Then enzymes actually work by lowering the activation energy for a reaction, and then it increases the rate of the reaction. And enzymes decrease the Gibbs free energy of activation, but they have no effect on the free energy of reactants. You see here the activation energy of the enzyme, and when you calculate it, this one is the steeper one, and then this activation energy without the enzyme. There's the reactants here, and then the product's overall energy released during the reaction. Then there are actually several factors that affect the enzyme catalyst reaction. So factors like let me increase this. Yes, so we have factors like substrate concentration, we have enzyme concentration, enzyme concentration. We have pH of the medium, pH of the medium. We have temperature of the medium, temperature of the medium. And we have effects of inhibitors on enzyme activity. It's like, for example, you have competitive inhibition and maybe non-competitive inhibition. You have effects of the inhibitors on enzyme activity. So when we talk about substrates, substrate concentration or concentration of enzymes, this just refers to like the rate of reaction, like when the rate of the reaction is actually proportional to, like look at this diagram, when the rate of the reaction is actually proportional to the enzyme concentration here, provided that the substrate concentration is at high level. So if the enzyme concentration is increasing, so as the enzyme concentration is increasing from this diagram here, the rate of the concentration would actually also increase. Then concentration of substrates This enzyme concentration. So here I talked about the enzyme concentration here. That's the second point. So the first point, which is substrate concentration of substrates, it just means like when there's an increase in the substrate concentration, there's a gradual increase. It gradually increases the velocity of the enzyme reaction within the limited range of the substrate level. So like a rectangular hyperbole, like this, a rectangular hyperbole, like you see in this diagram here, is obtained when velocity is plotted against the substrate concentration. Velocity is plotted against the substrate concentration, and there are three distinct phases of the reaction that is observed here. So like this, A is linear, you can see from here to here, from this point to this point is linear. Then B, there's a curve, and C, like this part, almost unchanged. So you can see, like maybe I can say this is A, this is B, and then this is C. Almost unchanged. And so when you look at this order of reaction, we see that like when the velocity of the reaction is almost proportional to the substrate, maybe we can call it S. Yes, when it's almost proportional to the substrate S, here, S would be less than the constant. So the rate of the reaction is said to be like this rate is now first order with respect to the substrate. So when the substrate concentration is greater than the constant, the rate of reaction is independent of the substrate concentration, and then the reaction is said to be zero order. So if we look at what's the next one? Okay, if we look at kinetics, enzyme kinetics and Km value, which is Michaelis-Menten's constant. Enzyme kinetics and Km value. So the enzyme E and the substrate S actually combine with each other. And once they combine, they'll form an unstable enzyme substrate complex, ES. It's an unstable complex for the formation of a product. The product will be E plus P. So this Q1, Q2, and Q. So here, like you can see that K1 and K2 and K3, they just represent the velocity constants for the respective reactions. Km, which is the Michaelis-Menten constant, or Briggs or Haldane constant, depending on what name you want to use, and it's given by the formula. And so this is the formula. Michaelis-Menten constant equals to K2 plus K1. So you can also see that check the velocity of BV is equals to V max. This brackets over the Michaelis-Menten constant, so at substrate concentration. And V here stands for like the maximum velocity. This S is the substrate concentration, and this Km is Michaelis-Menten's constant. So if we assume that the velocity is equals to half of V max, the equation will be the equation 1. Okay, because this is equation 1. This is equation 1. We'll just assume that equation 1 will be substituted, and we'll have half Vmax, which is equals to the Vmax of the maximum velocity of the substrate concentration divided by the Michaelis-Menten constant plus the substrate concentration. And then we have equals to 2 of the maximum velocity times the substrate concentration divided by the maximum velocity. And we will see that the Michaelis-Menten plus this S plus the surface concentration will just be equals to 2S, because obviously this will cancel this out. And finally, we would have, because we have 2 of this, once this comes to the other side, it subtracts by 1, equals to 2 of the concentration minus just 1 of this, and eventually we have this. The Michaelis-Menten constant will be equals to the substrate concentration. So K stands for the constant and M stands for the Michaelis. And so the Michaelis-Menten constant is now defined as the substrate concentration, which is expressed in moles per liter. So what to do is to produce half of the maximum velocity in an enzyme catalyzed reaction. And it indicates that half of the enzyme's molecules, which is 50%, is bound with the substrate molecule when the substrate concentration equals the Michaelis-Menten's value. So the Km value is a constant and the characteristic feature of any given enzyme. So it is a representative for measuring maybe the strength of the substrates of the enzyme substrate complex. Like a low Km value would indicate that there's a strong affinity between an enzyme and a substrate, whereas a high Km value will reflect a weak affinity between them. So for majority of enzymes, the Km value is usually within the range of like 10 to 5 to 10 to 2 moles. But it should also be noted that Km is not really dependent on the concentration of enzymes. Yes, it's not dependent on enzymes. If we talk about Lineweaver-Buck double reciprocal plot, here, here's the, okay. Yes. So that's Lineweaver-Buck double reciprocal plot. So in order to determine the, okay, we can see this value here. In order to determine the Km value here, the substrate the substrate saturation curve is actually not very accurate, since like the Vmax is approached like asymptotically. So one should take the reciprocals of the equation 1, then a straight line graphic representation is obtained. So if we have it like this, V equals to Km. over Vmax and the substrate concentration. So we have this times 1 plus the substrate concentration Vmax, substrate concentration, this one 2 over Vmax, the substrate concentration. So, and then finally 1 over V is equals to Km times 1 plus 1 over the maximum velocity and the substrate concentration by the maximum velocity. So this equation is like similar to those equations like y is equals to ax plus b. So a plot of the reciprocal of the velocity, that's the 1 over v, versus the reciprocal of the substrate concentration, which is 1 over the substrate concentration, will give a straight linear graph, just like what we see here. And the slope is km over Vmax, and the y-intercept is 1 over maximum velocity. It's actually much easier to calculate the km from intercept on the x-axis, which is like minus 1 from here. It's easier to calculate it from here, which is minus 1 over km. But further, like the double reciprocal plot is useful in understanding the effect of various inhibition. So like enzyme reactions with 2 or more substrates, the majority of enzyme catalyzed reactions involve 2 or more substrates. So even in the case of multi-substrate enzymes, like despite the complex mathematical expressions, the fundamental principle conform to Michaelis-Menten's kinetics. So if we look at the effect of temperature, if we mention it here. Yes, like if we look at the effect of temperature on the medium, so like velocity of an enzyme's reaction increases with an increase in temperature, like maybe up to a maximum and then it declines. So like a bell-shaped curve usually observed, like temperature coefficient or Q10 is defined as an increase in the enzyme velocity when the temperature is increased by like 10 degrees Celsius. So for a majority of the enzymes, Q10 is to between maybe 0 degrees Celsius and 40 degrees Celsius. And also an increase in temperature will also result in like a higher activation energy of the molecules and more molecular or like enzyme and substrate collision, and then there'll be interaction for reaction to proceed faster. The optimum temperature too, like for most of enzymes, which is between like 35 degrees Celsius to 40 degrees Celsius, like if for a few enzymes, maybe like TAC, DNA polymerase, like muscle adenylyl kinase, they're active even at 100 degrees Celsius. Some of the plant enzymes, like maybe urease, they have optimum activity maybe around like 60 degrees Celsius. And it can actually be due to like very stable structure and they conform to these enzymes. So generally, when enzymes are exposed to maybe a temperature above 50 degrees Celsius, they are denatured and it leads to like derangements in the native structure of the protein, and active sites is actually the same. So most of these enzymes become inactive at high temperature above 70 degrees Celsius. And what is this effect clinically? It just means that food can be preserved in refrigerators at low temperatures, like due to the reduced bacterial enzyme activities, like certain surgeries are carried out by lowering the patient's body temperature. So they induce hypothermia so that, and thus they'll have this metabolic rate. Then if we look at effect of pH, like what's the effect? Like an increase in hydrogen ion concentration would considerably influence enzyme activity, and a bell-shaped curve is normally obtained. So something like a bell-shaped curve is normally obtained too. And every enzyme or each enzyme has an optimum pH at which the velocity is maximum. And below and above this pH, the enzyme activity is usually much lower. And at extreme pH, the enzyme becomes totally inactive. So most of the enzymes of higher organisms, they show optimum activity around like neutral pH, which is between 6 to 8. And there are, however, many exceptions like maybe pepsin, which is like 1 to 2. The pH is 1 to 2, or maybe acid phosphatase, which is like 4 to 5, and sometimes some alkaline phosphatase, which is like 10 to 11. But enzymes from fungi and plants are the most active in acidic states, which is 4 to 5. So hydrogen ions influence the enzyme's activity. And how do they do this? They alter the ionic charges on the amino acids, particularly on the active sites, the substrates, and the enzyme substrate complex, and so on. Then if we look at the effect on products concentration, so accumulation of reaction products generally decrease the enzyme velocity. So for certain enzymes, the products actually combine with active sites of enzymes and they form a loose complex and then inhibit the enzyme activity in the living stream. And this type of inhibition is generally prevented by a quick removal of products formed. And effects of activators too. Effects of activators. If you look at effects of activators, like some enzymes require certain inorganic and metallic cations like magnesium, manganese, zinc, maybe calcium, carbonate, copper, sodium, potassium. And the likes for maybe so that it can have optimum activity. And rarely, anions are also needed for enzyme activity, so maybe like chloride ion for amylase. Metals actually function as activators of enzyme velocity through various mechanisms, and they combine with the substrate formation of the enzyme substrate metal complex and direct participation in the reaction and bring a conformational change in the enzyme. So we have like two categories of enzymes that require metals for their activity to be distinguished. So, that'll be metal activated enzymes, and metalloenzymes. So for metal activated enzymes, the metal is not usually tightly held by the enzyme and it can be exchanged easily with other ions. So for example, ATPase, which is magnesium and calcium and enolase. Then for metalloenzymes, the enzymes hold the metals rather tightly, which are not readily exchanged. So for example, you have alcohol dehydrogenase, you have carbonic anhydrase, you have alkaline phosphatase, carboxypeptidase, aldolase, which contains zinc, phenol oxidase, copper, pyruvate oxidase, manganese, xanthine oxidase, molybdenum, cytochrome oxidase, which is iron and copper. And then if we also look at effects of time, so under ideal or optimal conditions like maybe pH or temperature, time required for an enzyme reaction is usually less. Then variations in the time of the reaction are generally related to the alterations in pH and temperature. If you also look at the effects of, and talking about the factors that affect enzyme catalyze reactions. We just talked about effects of time. So if we now also we can also talk about effects of light and radiation. So exposure to enzymes. So if you expose enzymes to ultraviolet, maybe rays, beta rays, gamma rays, or even X-rays, they inactivate certain enzymes and due to the formation of peroxide. So UV rays inhibit salivary amylase activity. And the active sites of enzyme represents like a small region at which the substrate can bind and participate in the catalysis. So existence of active sites is usually due to the existence of active sites is usually due to the tertiary structure of proteins, resulting maybe like three-dimensional native conformation. The active site is also made up of amino acids, which are catalytic residues and are far from each other in linear sequence. Active sites are also regarded as clefts. They are also regarded as clefts or crevices or pockets that occur on like a small region in a big enzyme molecule. Active sites, they are not rigid in structure and shape, they are rather flexible and they promote specific substrate binding. Generally, active sites actually possess substrate binding sites and catalytic sites. So the latter is for catalysis of specific reactions. Then coenzymes or cofactors of some enzymes depend on they are present on part of catalytic sites. Substrate binds to active sites by weak non-covalent bonds. Enzymes are specific in their function due to the existence of active sites, and they are commonly found amino acids at active sites such as serine, aspartate, histidine, cysteine, lysine, arginine, glutamate, tyrosine. Among some of these acids, you have serine, which are also frequently found. Like substrate concentration binds to enzymes at the active site and they form enzyme substrates. Then the products usually released after the catalysis and the enzyme is available for use. So let's finally talk about enzyme inhibition. Enzyme inhibition. So enzyme inhibitors, they're actually defined as substances that bind to the enzymes and bring about a decrease in catalytic activity of that enzyme. So the inhibitor may be organic or inorganic. And we have three broad categories. We have the reversible inhibition, irreversible inhibition, and the allosteric inhibition. So for reversible inhibition, for reversible inhibition, inhibitor will bind non-covalently with enzymes, and the enzyme inhibitor can be reversed if the inhibitor is removed. The reversible inhibitor is now divided into competitive inhibition and non-competitive. So for competitive inhibition, the inhibitor they closely resemble like real substrates. They're regarded as substrate analogues. The inhibitor will compete with the substrate and bind at the active site of the enzyme, but it does not undergo any catalysis. As long as the competitive inhibitor holds the active site, the enzyme is not available for the substrate to bind. So, like the relative concentration of the substrate and inhibitor and their respective affinity with the enzyme determines the degree of the competitive inhibition. The inhibition could be overcome by be like the high substrate concentration. In competitive inhibition, the Km value increases whereas Vmax remains unchanged. Then for non-competitive inhibition, the inhibitor will bind to bind at a site other than the active sites on the enzyme surface, and this bind actually impairs with the enzyme function. Then the inhibitor has no structural resemblance with the substrate. So, however, they usually exist a strong affinity for the inhibitor to bind at the second site. In fact, the inhibitor does not interfere with the enzyme substrate binding, but the catalysis is usually prevented and possibly due to a distortion of the enzyme conformation. Then for irreversible inhibition, the inhibitors will bind covalently with the enzyme and inactivate them, which is irreversible. Then this irreversible is irreversible, which is irreversible. And these inhibitors are usually like toxic substances that poison the enzymes. And poison the enzymes. Then finally for allosteric inhibition, allosteric inhibition. This is when like an inhibitor hey, allosteric RIC. This is when an inhibitor would actually bind to the enzyme. All the active sites of the protein complex of the enzyme will undergo conformational changes. So the activity of the enzyme, as we can see here, the activity of the enzyme will decrease. So in other words, an allosteric inhibitor is a type of molecule which binds to the enzyme specifically at the the allosteric inhibitors. This is the allosteric site here. And on this other page, we see the allosteric inhibitor that is binding to the allosteric site here. And so that's it for our talk today on enzyme reaction rates and kinetics, the influence of xenobiotics, vitamins, and trace elements. I hope you've been able to get so much value. Just support by liking and commenting. Share a comment. What do you think? Talk to you soon. Bye for now.